Well, this is the second to last lecture, and I'm beginning to feel a little sad because after this, we won't have any more of these special meetings together. But think of all the free time you'll have after the final exam, after you get the final labs done too. But so we're picking up on the material we were just doing on the source coding. Okay, and so we have this concept of the rate distortion, the theoretical rate, and hold on. So the way it works is like this. So if you have any sequence of so you have a sequence of IID random variables, right? So it looks like you see of x 0, x1, it goes on. This is x n, okay? Right. So so you have that, okay? And you want to know you want to answer the question, what's the so you're going to have a coder. Right? The coder takes in one of these, well, actually what the coder will do is it can actually take a block of these things. It can code it to produce a Y. So these are IID. They're independent, identically distributed. So it takes a block of these and produces a Y, right? And this is the coder. And then you take this thing and you have a decoder. And it produces the decoded sequence. We'll call it Z0, Z1 through Zn, okay? And now there's some kind of distortion. So coder is Q. And then the decoder is Q inverse, okay? And there's some kind of distortion, and the distortion is the expected value of the distortion between x, say, xk, and zk squared, right? And you can average that. And so this is the distortion, right? And for a particular coder. And then m here is the number of bits, or k, I guess is the letter I used. K. So y here is a member of 0, 1 to the k. So it's a k-bit sequence that encodes n symbols. So you say, well, why not just encode one symbol at a time? Well, the answer is that, as I described last time, you can get better coding efficiency by coding multiple symbols together, even when the symbols are independent, which is really surprising to me, but it's nonetheless true. So you need to do that because we're talking about optimal coder. So if there's anything you can do to make it better, then you have to do that, or we won't achieve optimality. So in practice, what you lose by encoding multiple symbols together may be small in a particular application, but in theory, it can it's significant. So now the problem is what you want to really do is a constraint optimization problem. You want on a constraint for some distortion, for a coder with a distortion less than or equal to delta, right? You want to minimize, so subject to this constraint, you want to minimize. The bit rate, and the bit rate means you want to minimize k over n, because that's the number of bits per symbol it took, and we can call that r. Okay, so you want the minimum rate subject to distortion. So subject to a distortion constraint. So the question becomes, well, what's the best coder? Well, Shannon answered this question in a theoretical sense, and it's a constructive proof, but the proof depends upon a coder that's not practical. it's constructive. So in theory, so you'd say, well, you could use that coder that was used in the proof, but in practice, the coder that's used is a theoretical coder because it has exponential complexity to implement, so you can't really use it. But it is a constructive proof, and so the way that the argument goes is like this. First, you define a thing called the Rate-Distortion function. Okay, so first define R of delta. So R of delta is going to be a function. It's going to be the rate, the minimum achievable rate at a particular distortion level. So you tell me how much distortion you can tolerate, I'll tell you what the minimum bit rate is. You can produce a coder which uses more bits, but not less. Okay? So, and that's defined in a purely theoretical way based upon entropy, okay? So it's, okay? And then once I have this rate distortion, then there's going to be a theorem which says I can find, to next, theorem, there exists a Q, a coder Q, such that the actual rate and distortion is arbitrarily that's not spelled right. Arbitrarily close to R of delta. So in other words, at a distortion, say slightly more than delta, you can achieve a rate slightly more than R. So, and where slightly is as close as you want. So this is just like a limiting proof, right? In a limit, right, you let epsilon go to 0, right? So you can get as close to 0 as you like. In this case, you can get as close to delta and as close to R as you want. Now, you'd say, well, why not just make it as close, very, very, very close, right? Well, the answer is that there is a trade-off. As you get closer and closer to delta and closer to R, what you have to trade off is that the complexity of the coder becomes higher. So the block size becomes larger, which makes the complexity higher. In general, the coder gets more and more complicated. And also, remember that this is a theoretical model where these are random variables. Is a pixel in an image a random variable? No. It's just that's one of my favorite questions, huh? It's just a pixel in an image, okay? So this is a model for an image, or a model for a signal, or a model for speech, or a model for whatever, okay? So the theory of rate distortion is a beautiful theory, but it's a theory that applies to random variables and random processes. Real data is not random variables and random processes, but it can be modeled by it. So, for instance, one thing that drives me crazy when people will do is they'll say, I computed the entropy of the image. Well, gosh, if you computed the entropy of the image, I want to shake your hand, because that's very impressive, because the image isn't really a random variable, nor is it a random process, okay? It's just an image, okay? So you would have to have a direct line to the oracle in wherever it is the oracles live, okay? That can tell you precisely what the model for the image is, so you could compute that entropy. Usually it means, when someone says that, usually what they mean is they've made some simplifying assumption about the distribution. Like maybe they assume the pixels are independent, and they computed the entropy on their independence assumption, right? They used the sample histogram as a model for the distribution. Okay, so so that would be simple, but yeah, and the only thing you can ever really compute the entropy of is a random process or a random variable. Right? But you can try to compute estimates. You can try to estimate the distribution of real data and then compute entropy using those estimates. Okay, so but this is a very nice theoretical framework for understanding these problems nonetheless, but it's just important to understand the limitations also. So the theoretical definition of the rate distortion function is that you say, okay, subject to the constraint that, so x is a given random variable, okay? And then I find, now this is only x at one time, 0. I don't need to use a block here because this isn't the actual coder. This is just the definition of the rate distortion function. So then I say, among all random variables, and gee, there's a lot of random variables, right? Because, well, basically, I mean, well, without getting into a lot of details, the random variables are basically functions on probability spaces. So the set of all random variables is really saying the set of all functions. It's really measurable functions. So there's a lot. This is a very large set of things, okay? But I can ask for the infimum over I can look for the z, okay, that it produces the infimum, right, over all random variables of the mutual information between x and z, subject to some constraint on the distortion. And the distortion then, so if I made z equal to x, okay, then in that case the distortion, so if I set the random variable z equal to x, right, so let's take some special cases. So if z is equal to x, okay, in that case I pick the particular random variable. The random variable z is equal to x. And in that case, the expected value of the norm of z minus x squared is equal to 0, right? Because they're equal. But the problem is now the mutual information between z and x is going to be very large because z contains all the information in x. If x is a continuous random variable like a Gaussian random variable, this is actually going to be infinite. Okay, because right. So somehow you've got to try to pick a random variable that doesn't contain too much information about x, but is a good approximation to x. So one way of doing that is say to quantize x. So you want to look at among all random variables, the random variable that minimizes the random variable z, which produces a distortion less than delta, but has minimum rate. So this is a constraint optimization problem. The solution to that problem must exist because the infimum. So this is a set of scalar values because for every random variable, this mutual information is a number. So this is a set of numbers. Any set of numbers has an infimum. That's one of the basic principles of mathematics. Basically, it's like it's an axiom that the infimum always exists on any set. Okay? On any bounded set, the infimum exists, and this is a bounded set because the mutual information can't be negative, so it's bounded below. So the infimum exists, and whatever that is, that's the rate distortion. For every delta, we get a rate. Okay, now this could be just an exercise in just coming up with weird equations to write on a piece of paper to argue about their existence. But in fact, this definition is given meaning by the theorem, and the theorem says that if for any rate r prime that's greater than r, and for any distortion d prime that's greater than delta, there exists a coder. There exists an n, which is the block size, and there exists a coder, which is a deterministic mapping from these x's to a y, where y has k bits in it, okay, and k over n is less than r prime, and the distortion, the expected distortion between x and z is less than d prime. So it says that, and the way that the proof is based upon the generation of random codes. So interestingly enough, random codes attain the rate distortion bound. So by being just totally stupid, just doing something that has no structure at all, you achieve the rate distortion bound, and you say, well, wow, then that's like fantastic because it must be easy to build a coder that has optimal performance. Well, the problem is if you have random codes, then the decoder has no structure, and the only way you can do it is search through a set of all code books. So code means that it's a quantizer, so it's a vector quantizer. Basically what you do is for every code, you find an associated z, and then you map each x to the closest z. But the problem is the number of z's increases as 2 to the k, and if k gets large, then the size of the code book grows exponentially. And searching through the code book to find to encode the signal, or even decode the signal, because the decoder has to store the code book, becomes exponentially complex, and it's just not practical to do. And that grows. The exponential growth is very rapid, right? Because let's say that you want to code an image, so you use a certain block size, and the number of bits quickly grows to where 2 to the n just becomes impractical to do. There was a lot of interest in the early 90s and the mid 90s, maybe, in using vector quantization directly as a method for doing coding of images. And it's still useful for certain niche applications, but it's not so practical for a real coder. Mostly it's not used because of complexity issues. Okay, so now to make this a little more concrete, let me give you an example of a rate distortion function. The interesting thing is that rate distortion functions actually exist exactly for certain cases, and they give you a lot of insight. I won't try to derive them, but it turns out that you can theoretically derive the rate distortion for some examples. So I'll do example 1. So if we have x is a Gaussian random variable with mean 0 and variance sigma squared, right? Okay, so and we take the distortion d of xz to be equal to the expected value. So d, we'll have these as being, you can imagine these as being okay, so the rate distortion only requires that you have a single random variable here. But the theorem that makes it interesting is talking about coding a sequence of these IID random variables, each with the same distribution. And the reason you need that is because you need a block that can go to infinity. But we don't need to introduce this concept of the IID for just the point of calculating or the rate distortion curve. So this would be the expected value of x minus z squared. Okay, that's the distortion metric. And it turns out that for this case, it can be shown that the rate distortion curve has the following form. It's 1/2 log sigma squared over delta for let me see, sigma squared greater than or equal to delta squared, or greater than or equal to delta, I'm sorry, and it's 0 for sigma squared less than delta. Okay? Okay, so what does this mean? Well, the way to think about it, well, first of all, okay, so delta here is the distortion, okay? So okay, if, so let me see. If, consider if sigma squared is less than delta, okay? So delta is distortion. So I'll say here allowed distortion, because that kind of makes it more intuitive. So we're saying that we're going to allow up to a distortion of delta. Now, if the variance of the random variable is sigma squared, then we could take z to be just 0, right? So no matter so this is the way the decoder works. So you put x into one end, okay? It goes in the decoder, and the output is nothing, okay? It doesn't send anything. And then the decoder just outputs 0. So no matter what happens, you just output 0. You don't bother sending any bits at all. Now what happens is, well, how much distortion is there? So no matter what happens, I just go, what's the answer? 0. Okay? So then the expected value in this case of x minus z squared is equal to the expected value of x squared, right? And that's equal to what? Well, that's just sigma squared, because, well, that's actually a scalar value. I put a norm there, but it's just a scalar value. So it's just the expected value of x squared, which is sigma squared. That's what I said. I said it's a random variable with mean 0 and variance sigma squared. So basically, if I just always guess 0, the worst I can be wrong is, on average, sigma squared, because, you know, that's how much the thing varied in the first place. And the rate is 0. So rate of, in this case, delta equals 0, right? So that's this part of the equation. If sigma squared is less than delta, I just don't send any bits, and the rate is 0, and the distortion bound I meet. Now, if my distortion constraint is less than sigma squared, then in that case, I got to code something and send it. So intuitively, okay, now this is where I use the hand-waving argument, right? Now, if, let me see. So if sigma squared is greater than delta, right? Then think of delta. Think of the square root of delta as the quantizer step size. This is a very loose argument. In fact, the optimal quantizer doesn't have a uniform step size anyway. It's non-uniform, but this could be proportional to step size. So this is the size of each step in the quantizer. Okay. Now, if this is the size of the step, then the number of quantization levels is going to be sigma over the square root of delta, right? Because if the step size is the square root of delta and the standard deviation is sigma, then I roughly have this many, right? Now, you know, or times 2 or something, right? But, okay? Because this is just like how you design a quantizer. Is everybody following this? Okay, so N, M, K. I need some, I'll call this K, okay? So we have a K-bit quantizer. 2 to the, okay, so you have 2 to the B equals K. If you have an 8-bit quantizer, how many quantization levels is it? It's 2 to the 8 is 256. You have 256 quantization levels. And the output of the quantizer looks like this, right? Right? That everybody knows what quantization is, right? And the steps here are of size. The steps are of size the square root of delta. So if you have a standard deviation of sigma, okay, in the signal, and you're using quantization step sizes of square root of delta, how many of these steps do you need? You need n of them, or k of them, where k is sigma over square root of delta. Is that clear now? Okay. So how many bits how many bits do you need for this? Well, you need the log of that, right? The log base 2 of k should equal b, okay? And that's going to be equal to sigma over the square root of delta, right? But, okay, so, oh, I'm sorry, I left out the log here. Log, okay? So that's going to be equal to 1/2 the log base 2 of sigma squared over delta, right? Because I take sigma squared over delta, that's just sigma over the square root of delta squared. This is just the square of that. But I'm taking the log base 2, so I divide by 2. Is that clear? Do you want me to do that again? So, okay, so the ratio of sigma to delta is the number of quantization steps. The log base 2 of that tells me how many bits I need, right? So if I divide that by 2, then I can square the argument here. So that's the other part. If I take sigma squared over delta, I take the log and divide that by 1/2, and this should be base 2. Well, okay, if I don't take base 2, then this is in units of nats instead of bits. So nats are just like bits, only they're natural logs. Okay, so you can either use nats or bits. It's just a conversion factor. Okay, if everybody feels more comfortable, I'll just put a 2 there, and then we'll leave it in bits. Okay. So that would be units of bits. So this is the rate distortion in bits. So that was a totally hand-waving argument, okay? But at least now you have some intuition as to why this is the correct answer. So this is the theoretical rate distortion for the encoding of a Gaussian random variable with 0 mean and variance sigma squared. It's equal to this. And if we plot this, it looks like this, okay? So this is delta, or distortion. And this is rate. Okay. So what will happen is at sigma square, this touches. And as the distortion goes down, this will go towards infinity, because the amount of bits it takes to, this is the rate distortion plot, the rate goes towards infinity. Actually it's more common to plot the distortion rate plot than it is to plot the rate distortion curve. But people often talk about rate distortion. It's sort of the conventional term. But what's more commonly plotted in applications is the distortion rate. Distortion rate. So this has units of bits. So we have this is sigma squared. So what happens is that as you drive the distortion down, it takes more and more bits. It takes an infinite number of bits to drive the distortion to 0. But if you with a finite rate, with 0 rate, you have finite distortion. Okay, so this is R of delta for x distributed as 0 sigma squared. Okay?
Could you please show the previous slide for a second?
Does that make sense?
Yes.
Okay. Now, okay, example 2. And even this little bit of knowledge is useful when you're dealing with rate distortion functions. By the way, this function here, this function is monotone decreasing, right? So as you increase the distortion, the rate can only go down. It can't go up. And the other thing is it's convex. you can show it's convex because you could show that if you have two, one way of producing an intermediate, fact, I'll put here, facts, R of delta is 1, monotone, decreasing, 2 is convex. So the reason it's convex is that if you took two coders, okay, so you have one coder that achieves that performance point, and another coder that achieves that performance point. What you could do is 50% of the time use one, and 50% of the time use the other, and then the performance you would get would be the average of the two, and the average of the two would actually fall. So you have this point, you have this point, you draw a straight line. You can produce any point along there by just taking a randomized average of those two coders. And so you can show that, and so that's a legitimate coder, so therefore the actual rate distortion must fall below there. So you can prove that this rate distortion curve has to be convex. Okay, so it's a convex function. That's actually a very beautiful theory. If you take 642, the information theory, I think they go into a lot more detail on rate distortion theory. Okay, then what happens, so example 2, imagine that you have x, let's say 1 through xp, okay, each independent, and x, say I, is distributed as normal with mean 0 and variance sigma I squared, okay? So you have a set of independent Gaussian random variables, and each one has variance sigma I squared. Now, it's actually not too difficult to show. It's pretty easy to show because you can show this as a constraint optimization method. Basically, you can sort of think of this as being a coder. So you take a coder for each of. So you take a coder for each of these guys. Okay. So this is now coding of a vector instead of coding of a scalar. But again, you need to, in theory, extend this to be a sequence of these. Okay. Because you can't achieve the optimal rate distortion performance by just encoding one of these vectors. You have to have an infinite block of them and allow the block to get large, okay? But let's ignore those details. The rate distortion I can still define, right? And the rate distortion is then, I got to find the random variable z, which has minimum mutual information and achieves the distortion bound. So the distortion is now going to be equal to d of xz is going to be equal to the expected value of the sum from I equals 1 to p of the norm of the expected value of the norm of x, or I guess x I minus zi squared. So now I sum all these things to get the distortion. This is, I mean, I can pick any distortion metric I want, but for this distortion metric, okay, I can calculate the exact rate. So this is mean square error, or squared mean squared error distortion. So under a mean squared error distortion criteria, I can ask myself, well, what's the minimum rate? What's the rate distortion function? And it turns out that I can solve an optimization problem. Actually, you can solve this with Lagrange multipliers, because now what happens is that you can have an optimal coder for each of these x's, and the only thing that's unknown is what's the delta for that x, okay? So it turns out that it works like this. R of delta is equal to the sum from I equals 1 to P of the max of 0 and 1/2 log base 2 sigma I squared over delta. Okay, and D of delta is equal to the sum from I equals 1 to P of the min over delta I squared, sigma I squared in delta. Okay, so this is the intuition. Let's say you have a bunch of random variables. So this is I, okay, and it goes from 0 or 1 to P, okay? And I'll order them from largest to smallest. So this axis here is going to be sigma I squared. It's the value of the variance. So the variance is going to start off large. I just ordered them. They, there's some ordering. Okay? Now, if I want to go code these, I'm going to pick some quantization level, right? So this thing, so the quantization level, so sigma here is equal to or delta here is equal to like the quantization step size squared, intuitively. This is just an intuitive understanding of the equations. So for that quantization step size, I draw a line here, right? And for any random variable which is less than delta, I just accept that distortion. I just don't code it. I just throw those I quantize it to 0. I get rid of those variables, okay? I just don't send these. There's no reason to send them because they're already fell below my distortion criteria, okay? For the ones above that value, I have to code them. So I take the ratio of sigma squared sub I and delta. I take the log base 2 and take 1/2 that because this is energy, and that's the number of bits. So for each variable, for each of these variables, okay, it's 1/2 log base 2 of sigma I squared over delta, right? So this is the number of bits. If that's greater than 0, that's what I have to send. If it's less than 0, it means that this thing fell below the value, right? So I take this, I take 0, and I take the max of that. And that's how many bits I have to send for that component. So this is the rate. You might call this R sub I. So it's the rate for the ith component. It's the number of bits I have to send for the ith component. The distortion is going to be, well, the distortion will be either sigma, it'll either be delta, I screwed that up. Okay, it'll either be delta, okay, but if delta is larger than sigma, I just accept the distortion of sending nothing, so it's going to be sigma I squared in that case, so it'll be the minimum of those two. Whichever one is smaller, that's what the distortion is going to be. That'll be di, right? And now the total distortion is the sum of all these individual distortions, and the total rate is the sum of all those rates. So that's why this is the expression for the rate distortion when you have a vector of independent Gaussian random variables with mean 0 and variance sigma I squared, right? Does everybody follow that? Now, what's interesting is now you can generalize that further. You say example 3, right, is let's say I have a vector, a Gaussian random vector, okay, which is of dimension p. And the expected value of x transpose, is equal to R. That's the covariance matrix. And the expected value of X is equal to 0. So X is distributed as normal with mean 0 and covariance R. Now, because you guys did the lab on eigenimage decomposition, you know that R can always be decomposed because it's symmetric and positive definite. It can always be decomposed, and it's going to be E lambda E transpose. This is the orthonormal eigen decomposition matrix, right? This is diagonal, and its values are lambda 1 through lambda I. These are the variances of each decorrelated component. That, by the way, was the whole idea behind the eigenimage lab. That you take the images, you try to estimate the covariance, and then you transform the image into a space where each component is independent, is uncorrelated. If it was Gaussian, it'd be independent. They're uncorrelated. And then, right, so then you have the uncorrelated data. Now, I can calculate the rate distortion for encoding this vector, which is potentially correlated. So it's a Gaussian random vector with arbitrary covariance R. And forget about the mean. The mean doesn't really matter for rate distortion, right? Because you can always subtract the mean off. It doesn't, with no bits. So in this case, the rate distortion R of delta is exactly the same as it was in the last case. It's the sum from I equals 1 to P of the max of 0 and 1/2 log base 2 of, now this becomes lambda I over delta. Because lambda I is just the variance of the ith component. It's exactly the same case as in example 2. Because here I just assumed I had independent random variables that were uncorrelated and different variances. But I can always do, this was exam question 2, something like 2C or something like that. The X tilde is equal to E transpose X. This will be decorrelated. And in that case, the expected value of X tilde transpose will just be lambda. And mean square error distortion in this domain is the same thing as mean square error distortion in this domain because it's an orthonormal transform, right? Orthonormal transforms preserves distance. So therefore, mean square error in both domains is the same. So now it's just immediate that the rate distortion is the same formula as I use here, but I just use, instead of the sigma squares, I use the lambdas. Okay? So, does this seem reasonable? Do you understand what this means? So what this means is if you want to find the rate distortion for some vector x, compute its eigenvalues, plot them out in a plot like this, and then see how many fall below your threshold. The ones that fall below the threshold just get zeroed out. The other ones have to get encoded. Right? Okay? Any questions about this?
Should that be lambda?
Oh! Yes, this should be lambda. Oh, that was horrible. I got carried away. Yes, thank you. Good. It means you understood what I'm talking about. Okay? Good. Okay, now I'm going to take it one step further to example 4. Okay, so now what you can do is this. You can say, oh, okay, and here I'm basically going to just use hand waving because there's a whole bunch of different things you have to prove. You have to say, well, okay, let's say you have a random process. Now, xi, okay? with autocorrelation function, so the expected value of xi is 0, okay? And the expected value of xi plus k equals r sub k, and then s of e to the j omega is the power spectrum, is the discrete time Fourier transform of r of k, right? Right. So now this is a Gaussian random process. Gaussian random process. Zero mean Gaussian random process, and it's stationary. Okay, it's wide-sense stationary, it's strict-sense stationary. It's got its autocorrelation function is r of k, and its power spectrum is s of e to the j omega, right? So you could say, well, what's the rate distortion for this Gaussian random process? So I want to know how many bits per sample I need in order to achieve some mean square error distortion. So we'll have the distortion of xz is going to be equal to the expected value of xi minus zi squared, right? And then what's the rate? Okay, so I'm going to use a mean square error distortion. Well, the answer is, and I'm going to basically give you the answer, but it requires that you sort of imagine, what you want to do is now take finite subsequences of this random process, compute the autocorrelation function, then do an eigen decomposition. It turns out that the eigenvalues of the autocorrelation matrix for a subsequence are basically very close to the power spectrum. That's why people talk about the spectrum of a matrix being its eigenvalues, okay? There's a very close relationship between the power spectrum and the eigenvalues of the autocorrelation matrix. So what ends up happening is that you can use the theory I had before, and the answer that becomes that the rate looks like exactly the same kind of formula. There's some normalizing constants and such and all this kind of gobbledygook. But in the end, what you get out is this. So you get an integral now instead of a sum, and the distortion looks like this. Okay, and I have 1 minute, so I have to draw the picture. So what happens is you get like a rate distortion that looks like this. So if you have some power spectrum, this is pi, this is 0, and this is the power spectrum. Right? So this is s of e to the j omega, and this is delta. Basically, you get rid of these coefficients. You get rid of the coefficients that fall below the threshold. You don't bother quantizing them. And these, the number of bits you have to allocate per sample, is related to the ratio of delta to s. So it's the same argument. You're right? Okay, and that's pretty much how it works. So next time I'll talk about the Jpeg Coder and some of the particulars of how it works. In Jpeg, you actually take a DCT, which is, the DCT is being used as an approximation to the Carhoon-Loew transform. So it's basically calculating this decorrelated x, and then a quantizer is applied, and the ones that come out to 0, you just run length code. You don't send those coefficients. So it really does something very similar to what this theoretical rate distortion method prescribes, right, in concept. Of course, so this theory gives you a lot of insight, I think, into the problem. It's valuable. So, okay, one more class, and then the final exam, and then you can all go off and party. So, okay, bye.